This video will start chapter 9, which is on acids and bases. We will start with section 9.1, which is an introduction on acids and bases. So acids on the left side of this table, what are their properties? They have a sour taste. Think about lemons, for example. Acids dissolves metals, so metals are solids, and if you put a piece of metal into a liquid acid, they will completely dissolve and become aqueous ions in a solution. Acids neutralize bases in reactions that we call neutralization reactions. And the blue litmus paper turns red when it's in contact with acid. So it's an easy way to know if you have an acid or not. Examples of common acids are the hydrochloric acid, HCl, which is synthesized in our stomachs. So the stomach produces HCl to digest food. Acetic acid is another acid that you find in vinegar. And citric acid is an acid that you find in the citrus fruits. Bases. So the properties of bases are they have a bitter taste. They feel slippery, so think about detergents. They feel slippery. Bases neutralize acids in that neutralization reactions we talked about. And to detect a base, you can use a red litmus paper and it will turn blue if it is in contact with a base. So common bases are sodium hydroxide, NaOH, found in a lot of cleaning agents. Sodium bicarbonate, NaHCO3, is more known as baking soda. And then the ammonia, NH3, is also a base, found also in cleaning agents. So the Bronsted-Lowry definition of acids and base. And so Bronsted and Lowry are two scientists, a Danish and an English scientist that at the same time came up with this theory for acids and bases. And so that's why the definition bears both names. And so they came up with this definition for acids. An acid is a proton donor, and a proton is an H+. And a base is a proton acceptor. So why H+? A proton is H+, because H is hydrogen. Hydrogen is the first atom listed in the periodic table. And it has atomic number 1, so it's made of 1 proton and 1 electron. And when you remove this electron from the atom of hydrogen, then you have only 1 proton. They don't even have a neutron. So that's why it's called a proton when it's the hydrogen atom without an electron. The positive charge comes from the fact that you have removed an electron. So H+ is called a proton because that's basically what it is, a proton. So an acid is a proton donor and a base is a proton acceptor. So note here that H+ does not exist in water by itself. Instead, it reacts with water to form the hydronium ion, H3O+. H3O+ is a polyatomic ion that you may have seen in your list of polyatomic ion. And so when you have the H+ in water, it will combine with the molecule of water. And you know that the molecule of water has 2 lone pairs on the oxygen. And so the one of the lone pair can be shared and make a bond with the hydrogen. And so then water becomes the hydronium ion that has 3 bonds, 3 single bonds to the 3 hydrogens, and then 1 lone pair on the oxygen. And so that's a positively charged ion because H+ came with no electrons, so it's deficient by 1 electron. And so that's what is actually present in aqueous solution. It's the hydronium ion, not the proton. So the Bronsted-Lowry acid-base reaction, so if we combine the fact that the acid is a proton donor and the base is a proton acceptor, then a Bronsted-Lowry acid-base reaction is when the acid molecule donates a proton, an H+, to the base molecule. So there is a transfer of proton from the acid to the base. So let's look at this generic form of an acid-base reaction. So let's look on the left first and only focus on HA, the acid. So H with single bonded to A is an acid in its generic form. And so it's an acid. We know this because there is H as first element in the formula. And that first H is the acidic hydrogen. It's the hydrogen that the acid will donate. And so an acid is a proton donor, which means it will lose that H+. So you see why it branches out as loss of H+. And so when the hydrogen leaves the acid, it leaves behind the electrons. So the electron pair that is between the H and the A will stay with the A. And so then you will have H+, and then A will be A- with the lone pair. So the bond becomes a lone pair on A, and then there is an extra electron for A, and it's showing up as a negative charge. So the acid, when it donates a proton, it becomes the A- electron, or the A- ion with one negative charge. Now let's focus on the base, what's in blue here. The base is a proton acceptor, which means it has a lone pair. It has to have a lone pair, so the base must have a lone pair to accept the proton. And so that lone pair will be used to form a bond with the proton. The H+, will grab on that lone pair and form a bond with B. So if you see on the right now, it becomes H single bonded to B, and the H+ comes with a positive charge. So that's why overall HB is positively charged, because hydrogen came without electrons, and so HB is deficient by one electron. And so when you put an acid and a base together, then overall an acid-base reaction is corresponding to the transfer of proton from the acid to the base. So let's look into more detail into Bronsted-Lowry acids. What are they? So a Bronsted-Lowry acid is a proton donor, so that means it must contain an hydrogen atom. And so by convention, this hydrogen atom that will be acidic is written first in the formula. And so a given acid can donate more than one proton. And so if it donates only one proton, we will call it a monoprotic acid when it contains only one acidic proton. So HCl, for example, is a monoprotic acid. A diprotic acid contains two acidic protons, like H2SO4, the sulfuric acid, has two acidic protons, and they leave one at a time. A triprotic acid contains three acidic protons, like in H3PO4, the phosphoric acid has three acidic protons. And notice how each time those hydrogens are written first in the formula of the acid. Otherwise, a Bronsted-Lowry acid may be neutral, or it may carry a net positive or negative charge. So there is no convention. It can be neutral like HCl, positive like H3O, like the hydronium ion, or carry a negative charge like HSO4, -1, the hydrogen sulfate ion. So another example that is not written here is acetic acid that we saw in the first slide. HC2H3O2. So you see that there is H first in the formula, but there is also other hydrogens in the formula, and so we put forward the acidic hydrogen in the formula, and that's the one that will be given away or donated by the acid. But an acid can have hydrogens elsewhere in its formula. So Bronsted-Lowry bases. So as we said, a Bronsted-Lowry base is a proton acceptor. And so to be able to accept a proton, a base must contain a lone pair of electrons. That lone pair of electrons can be used to form a new bond to the proton. And so here, let's look at the left side of this reaction here with NH3. NH3 is the Bronsted-Lowry base on the left here. And so ammonia, this is ammonia, has a lone pair on the nitrogen. And so that lone pair is going to make it a base because that lone pair can accept a proton. And here, if you place ammonia in water, water will act as an acid and donate an H plus to ammonia. And so if you use that lone pair and make a bond with the H plus, then you obtain what's on the right of the arrow, and it's NH4 plus, NH4 plus, the ammonium ion. And that's what ammonia becomes when it accepts a proton. And so water here in this example acted as the acid by donating an H plus. And when water donates an H plus, it becomes the OH minus ion, the hydroxide ion. So that's why on the right now, water has become OH minus. So common Bronsted-Lowry bases, so symbolized in a generic form by B with a lone pair. And so bases must have lone pairs, and for example, neutral compounds like ammonia and water can act as bases because they have lone pairs. You see them in blue here to show how that makes them basic. And then bases are mostly made of the hydroxide ion. So all those strong bases are containing the OH minus, the hydroxide ion, and that's what will be the base in each of these metal salts. So the hydroxide ion can be combined with any kind of alkali metal or alkaline earth metal. So like sodium, potassium, so from group 1A, from the alkali, sodium, potassium, lithium, rubidium, cesium. When they are bonded with OH minus, they make bases. And from group 2A, the alkaline earth metals like magnesium, calcium, strontium, barium, they also make ionic compound with OH minus, and these ionic compounds will be basic. So let's go through this learning check where we will decide if the formulas that are given are acids or basic. So pause the video to think about this by yourself before you watch the answer. So H3PO4 is an ingredient that is found in soft drinks. So is it an acid or a base? And H3PO4 is an acid because you have H as first element in the formula. And this is phosphoric acid in particular. It's found in Coca-Cola or all kinds of soft drinks to preserve the drink. NaOH is used in drain cleaners. So is this an acid or a base? And here NaOH contains the hydroxide ion. It is sodium hydroxide. You see the Na plus and OH minus ions combining to make this NaOH formula. And so when it's placed in water, the hydroxide ion will be a strong base. And that's why it's used in drain cleaner. It really is a strong base. MgOH 2 times, that is used in antacids. So as it says, it's antacid, which means the contrary of acids are base. And so that's a base also, and it's a magnesium hydroxide, also containing the hydroxide ion, which makes it a base, a strong base, because the hydroxide ion is a strong base. And then HNO3, is this an acid or a base? And that's an acid, it's a nitric acid. And we know it's an acid because we see hydrogen as first element in the formula.